ASEAN. I am the director of the Columbia University Superfund Research Program. I am a faculty member in the Department of Environmental Health Sciences at the Mailman School of Public Health. And we are very excited to be together today to resume with our Monday seminars at the Columbia University Superfund Research Program. And as many of you who are familiar with our seminars know, we generally have two sessions. In the first hour, we generally talk about health, environmental health, often related to arsenic or other metals. In the second hour, we do generally focus on earth sciences and environmental sciences. And the order can be either way, but we generally have 1 hour health and 1 hour environment. Today is going to be a little bit different, although we are going to be talking about health also in one of the speakers' presentations, but really we are going to focus quite a bit much more on the environmental side. And also the main difference today is actually the fact that we are all remote. Generally, our seminars include an on-site component with all of us from the Columbia University who come together once a month from the different buildings and parts of the university where we all are. But today we cannot come together, so we all have to join together remotely. The good thing about that is that we are now in the same position as many of our external participants who very often also join us remotely. So we are all together on the same boat today, all of us following from far apart, but together in following the science. So now that we have, I believe most of the participants have joined, I am really delighted to introduce our first speaker, who is Dr. Kathrin Schilling. She's an associate research scientist at the Lamont Doherty Earth Observatory at Columbia University. And as a brief introduction, she did her undergraduate degree in geology at the University of Leipzig in Germany, followed by a PhD in social sciences and microbiology with Johannes Gutenberg University, also in Germany. As for her PhD, she got an Excellent Scholarship Award from the German Research Foundation. She followed her doctoral work with postdocs fellowships at Utrecht University, UC Berkeley, and Oxford. And in April 2019, she joined the Lamont Doherty Earth Observatory at Columbia. So she has done very important work related to metals and metals isotopes, and she received the Metallomics Young Investigator Award. And today she's going to be talking about what can we learn from selenium isotopes and what selenium isotopes can tell us about environmental processes and human health. So Kathrin, please, the floor is yours, and I hope we can hear you well.
Okay, yeah, let me know if you can hear me. Thank you, Anna, for the lovely introduction. And I'm really excited to give the talk at the Superfund seminar. And I hope everyone is well. And if at some point I might have to turn on the light because I'm in the UK and it's already 8 p.m. So if the lights condition might change, it's just because it's getting dark, I think.
So Kathrin, 1 second, because I forgot. For people who are listening, as you have questions, please write our questions in the chat. And then we can read them at the end of your presentation. We'll read them in the order that they arrive. So please, as you see a question that you have as the presentation goes on, please write it in the chat, and then we'll go over them at the end.
Okay. So as Anna mentioned, today's talk is not on arsenic, but it's an element which is really close to arsenic. If you look at the periodic table in my starting slide, you see it's right next to arsenic, it's selenium. And I'm an isotope geochemist, and I worked for a long time on selenium. And my talk is going to focus on how we can use selenium isotopes to understand environmental processes, understand how selenium cycles in the environment, and understand the impact to the human health. So Oops, let me see. Okay, here we go. So first, I would like to give you a background on selenium, what the chemistry of selenium, and how we can use isotopes to understand processes in the environment, how isotope in general fractionates. And then I will go to 2 examples how I use selenium stable isotopes to understand the cycling of selenium. First is a case study I did in India, in Punjab. It's a contaminated agricultural site. And here I try to understand how selenium moves from the water to the soil to the plants. And in the second example, I show you how we can use selenium stable isotope as an indicator for post-mining selenium reduction in an uranium roadfront deposit. The painting on the left shows you, it's a painting by Nicolas Passin, which shows you Selene and it's called her lover Endymion. And this piece of art you can see in the Detroit Art Museum. It's actually very interesting because Selene is the goddess of the moon, and she's immortal. And he is a shepherd, and he is mortal. And she wanted him to live forever and have a long life and healthy life. And that actually connects me to the next slide, why selenium is important, because selenium is essential for human health. So what we know is selenium is a part of our 21st amino acid, selenocysteine. So a lot of you might be familiar with cysteine. This is the amino acid with sulfur. Here, sulfur is replaced with selenium. And it's very important as an antioxidant to capture all the radicals in our body. And we normally get enough selenium from our food and the water, but about 0.5 to 1 billion people have low intake of selenium. Low intake of selenium means less than 20 micrograms of selenium per day. But you can buy selenium as a supplement. You see that on the left. You can buy them in all pharmacies and grocery stores. And a few years back, I went to China, and they advertise products which are enriched in selenium. These are teas, and even they have selenium enriched wine, which is like below it basically says selenium enriched wine. On the right, you see simplified cycling of selenium in the human body. Basically, that selenium is incorporated in enzymes. So we take up selenium, as I said, from the food or from the water. In the food, it's definitely complex. In the water, it's mainly in its oxidized form, selenium-6 or selenium-4. In the body, it gets reduced to selenium-2 and incorporated in selenocysteine. And any excess of selenium is then excreted by urine or the breath as either methylated form or any other form of selenium. But selenium is also toxic. And it becomes toxic, or the WHO considers it as toxic, if you have a daily intake of more than 400 micrograms per day of selenium. That has different effects. So if you, what I said, it can inhibit the cell growth. It can inhibit the cell proliferation. It also can damage the DNA. And this is a photo on the bottom where you see the hands of someone that was taken in India, in Punjab, actually the field site I studied, where people showed effects of brittle nails and loss of hair. But more than we know about selenium poisoning to humans, it's very toxic to the wildlife. And it has been shown, like in the 1980s, it got very aware, people got aware of it in the Castleton Valley in California, where the birds were poisoned by selenium. And there were a lot of studies out to find out how selenium cycles in that area. And they even kind of closed down the entire area to rescue the wildlife. And the selenium is how selenium is poisoning or toxic depends on its oxidation state, because the mobility of selenium is determined by its oxidation state. So if we look at the left, there's an EH-pH diagram of selenium. So we have the pH at the x-axis and the redox potential on the y-axis. So if we look between the pH between 6 and 8, which is basically the pH condition we have in most environmental settings, then we see at very oxy condition, we have selenium selenate, which is selenium 6+, the highest oxidation state. It's very mobile, and that's why it's highly bioavailable. And it's basically the most toxic form of selenium in the environment. So then right below, in mildly reducing condition, we find hydroselenite, so selenium +4 or selenite. And then below that, when we go to further reducing condition, the orange zone is basically elemental selenium, that it's a solid and immobile, and further reducing condition, then we would find selenium -2, and that normally precipitates with other metals to form mineral forms like copper selenite, mercury selenite. This is also immobile, and because it's less mobile, it is less toxic. So if we go to the right, we see, to simplify that a little bit in the environment, then we go from pH, we have again pH on the bottom, and then we have the redox potential. But now we also bring into account like some, when we look at the soil, complexation with organic matter, clay, or iron oxide. So what we see here, we don't have to worry much about elemental selenium or selenite, because they're like under reducing conditions, and they're most of the time they're solid and immobile. But we are more worried about the oxyanions, and they behave, the two oxyanions, selenium 6 and selenium 4, behave slightly different. Selenium 4 has a strong affinity to absorb on organic matter, clay, and iron oxides, where selenium 6 doesn't. So that's why selenium 6 is the most mobile form, most toxic, and as most bioavailable, and then also most toxic form of selenium. And I will wait until you take a photo. Okay. The selenium cycle has been impacted by the human activity over the last decades, because what we see normally, selenium in most geological settings, it occurs in a reduced form, which means elemental selenium or selenium -2. And here are three geological settings where we find a lot of selenium. That's coal has a lot of selenium, alluvium, and of the roll fronts. And coals, because of mountaintop mining, for example, in Canada, a lot of selenium is released. In the alluvium, irrigation causes the release of selenium, and in the road front, it's the in situ recovery mining. And what it does, because of the change of the oxidation state, the reduced form getting oxidized to the oxyanion selenium 6 and selenium 4, which I said before, are highly mobile and therefore more bioavailable and more toxic. And that had a huge, and here are a few examples from recent reports from the EPA in September 2019, that from a river they found high concentration of selenium and nitrate. And also an article in the Washington Post in September 2019 reported selenium pollution were found in the US rivers caused by the coal mining in Canada. And all this has huge impact on what I said, and on the wildlife and humans. So selenium is detrimental to aquatic wildlife. You see there are several papers out that show the deformity of fish. It's also toxic to honeybees because of the biotransfer from the pollen to the bees, because the pollen accumulate selenium. And of course, it's at higher level also toxic to humans. So, but what could be the solution if we now release, because of human activity, we have released a lot of selenium in its highly bioavailable form to the environment? What could be the solution for like kind of make it less bioavailable? And going back to the 4 oxidation states, so we have selenium-6 and selenium-4, the oxyanions, highly bioavailable, and then the 4 reduced forms. So the most obvious way is basically we reduce selenium-6 and selenium-4 back to a reduced form, elemental selenium, or even further to selenium-2, because that reduces the bioavailability and therefore the toxicity. So, but then if we do that, or if like natural remediation happens, then how can we track if these bioavailable selenium oxyanions are really reduced? So here on the left, you see a profile, a sediment profile for selenium-6 and selenium-4 with steps. And you see here that selenium-6 and selenium-4 drops basically to 0 below 5 centimeters depth. Okay, you can say that could be an indicator for reduction, but maybe there are other processes. As I said, selenium-4 can be strongly absorbed in iron oxides or on organic matter. So how can we make sure it's really reduction? Because that's the best way to immobilize selenium. And maybe just looking at the concentration is not always the best way, because the concentration, a change in concentration can also be affected by the dilution, dispersion, or, as I said, adsorption. Here, I would say maybe isotope can help. And this is a slide just say a bit of basics on stable isotope geochemistry. So it's a field which was established in earth sciences, but now slowly also is used in other fields like life sciences, biology, ecology, and more recently also in the biomedical field. You have the periodic table here, and what you see is like the ones which are circled in light green. These are the so-called traditional isotopes, so they're used for a very long time. It's hydrogen, carbon, nitrogen, oxygen, and sulfur. I think most of you might be familiar with those. And then the light blue ones are the ones they call the non-traditional stable isotope systems. And these are relatively new, that they're used, I would say, the last 20 years. And among them, you see it's also selenium. And now a little bit about selenium isotopes. So selenium has 6 stable isotopes. You have the diagram on the left. So we have 6 stable isotopes in the mass fraction, the natural abundances. You see the most abundant one is selenium-80, and the least abundant one is 74. But what we do, we are measure ratios of these abundance of these elements using a multi-collector ICP-MS. And the ratios we are measuring is 82/76. I can explain later more why these 2 isotopes. That has something to do with how we purify the samples before the analysis, and something about the instrument setting, which makes that the 2 ideal isotopes to the ratios to measure. So what we basically measure is the 82/76 in a sample relative to a standard. Here it's the NIST 3149 standard, and is as this shift from the mass fraction from the natural abundances is very, very small. We multiply that with 1000 and report it as a delta notation in per mil. So keep that in mind. So everything what I'm talking about isotopes, it's always referring to 82/76. And what we say, 82 is a heavy isotope, 76 is the light isotope. So just why isotope fractionates. So isotope fractionates because that's a process between the 2 isotopes have a different react differently. And there's a partitioning between two phases. Imagine a liquid phase and a solid phase. As I said before, selenium-6 is an aqueous phase, and we want to have it in a solid phase in elemental selenium, so that would be the partitioning. And the heavier isotopes have a stronger bond than the lighter isotopes, and that's you see in the graph here. So the bond depends on the bond length. So you have 82 selenium and 76 selenium.
What's happening?
And selenium 76 to get a reaction, that a reaction is happening, it has to go over this ramp here, and it's much easier to break a bond with 76 than 82 because it requires less energy. So if you imagine it's a reduction is happening, so the bonds for 76 break faster, so that's why an enrichment of 76 would be in the product and 82 stays in the reactant. To go how the isotope fractionates, there are actually two ways. Either it's an equilibrium isotope fractionation or a kinetic isotope fractionation. Let's start with the equilibrium. So imagine a bottle of beer where you have the liquid phase and you have a gaseous phase where your CO2 accumulates. So what you have a constant exchange between the liquid phase and the gaseous phase. And what it does is basically equilibrium, it exchanges as long until the heavy isotopes are going to be in the stronger bonds should be in the liquid phase, and the lighter bonds, like with the lighter isotopes, should be in the gaseous phase. That shows basically the diagram below. That can also be depending on redox states. It can also say when you have selenium-6, selenium-4 exchange, so the stronger bonds should be at the higher oxidation state compared to the lower oxidation state would be at selenium-4. But what we are looking at mainly is the kinetic isotope effect that's on the right-hand side. So the same thing, so you have the man, he has a glass of wine, but imagine it's a glass of bubble. So a sparkling wine or so it's like it's open, so the CO2 constantly removes, or he drinks it. So what it does, he removes basically constantly, so the lighter isotopes react faster, so are removed from the glass. That's going to be the product if you would measure the atmosphere, but in the reactant in the glass should become isotopically heavier with time. How we can measure these isotopic fractionation, and I just focus on the kinetic isotope fractionation, and we can determine that looking, most of the time it's done in experiments with either, for selenium is with microbes or with mineral phases. What we do, it's in a closed system, that means in a bottle, and for that we can apply the Rayleigh distillation model, and this is basically the diagram here. So what you have a reactant which is 0% is reduced up to 100%. It's on the x-axis. On the y-axis, you see the isotopic composition. So this delta values 82 selenium. And as you see, with progressive reduction, so as more selenium goes into the product, the reactant becomes isotopically heavier. And based on that, you can derive the magnitude of isotopic fractionation epsilon. And we have here, for example, we have two epsilons. One would represent a light, I would say it's pinkish, it's 2 per mil, and the red, no, it's 5 per mil, and the red line is 2 per mil. So if we now measure in a sample, let's say we measure a delta value of 4 per mil, and then we can draw the line, you see the arrow, and then going down, and based on, if we know the magnitude of isotopic fractionation expressed as epsilon, then we can say how much of the reactant was already reduced. So the isotopic fractionation can tell, basically, or the isotopic ratios could tell us about the extent of a process and a reaction in the environment, what a concentration can't. So for selenium, we have different processes causing different isotopic fractionation. What I said before, if there is a coordination change, or if there's a breaking of bond, like for we have reduction, then the isotopic fractionation is larger. So I divided it in redox reaction and non-redox reaction. and we have on the x-axis like no fractionation would be 0 on the right, and then the largest fractionation minus 20 per mil on the left. So what we see, there's a large range. So we have abiotic reaction using selenium-6 or selenium to selenium-4 with HCl. That's not relevant for the environment, but just was the first experiment have been done. And they show a large range of fractionation. When we look at selenium-6 or selenium-4 reduction by mineral phases, these are green rust or iron sulfide, and the fractionation is about 10 per mil. Then microbial reduction has been, there are 2 studies, they looked at different microbial species and the reduction, and depending on the reactant, if it's selenium-6 or selenium-4, and if the microbes can reduce it to either elemental selenium or just to selenium-4, there are different extent of fractionation. You can see these are the purple lines. So the largest variation was observed for selenium-4 reduction to elemental selenium. But anyway, all of these redox reactions cause large fractionation. If we can compare it to the non-redox reaction, this would be adsorption. Let's say adsorption of selenium-4 on iron oxide causes a fractionation of less than 1 per mil, and plant uptake causes a fractionation of maximum 1.5 per mil. And going back, taking just the redox reactions, then we see for the redox reaction, we basically see, that if we have a 2-electron transfer from selenium-6 to selenium-4, then we have a biotic, for biotic reaction, we see a fractionation of 2 to 7 per mil, for abiotic about 11 per mil. That's basically the mineral phase, what I showed earlier. For the reduction of selenium-4 to elemental selenium, a much larger fractionation is a 4-electron transfer. And for the selenium-6 to elemental selenium, we see a fractionation of between 9 and 12 per mil. It's a 6-electron transfer. Oops. And did I skip a slide? Okay. And I'm over the last few years, so these are the numbers of publication came out on using selenium stable isotope as a potential indicator for redox reaction. And we clearly see that over time, the numbers of publication increased. That's basic. It's mainly related to the instrument. The more we get better precision on the isotope analysis, better instruments, and more labs have the instruments, but also it's understood it's a very powerful tool to use selenium stable isotope to trace redox reactions. And here just a few examples. It's very common to use selenium stable isotopes to trace selenium in to understand the Pauli redox condition. And and also that's basically to understand when there was oxygen in the atmosphere, the development of the biosphere. But what we are interested in is basically more how we can use selenium stable isotopes in the modern environment and trace the redox cycle of selenium. And now I would like to come to the first study I did at the contaminated site in Punjab. This was a study I did during my time at Utrecht University in collaboration with University of Illinois and Punjab Agricultural University. So Punjab, that's the map in India, and Punjab is a northwestern state in India. It's very close to the Pakistan border. The study site, you see the star here, that's basically where it's located. Punjab is the state, it's mainly agriculture there, a lot of farmers. They mainly grow wheat, cotton, and rice these days, and but they changed their cropping system during the Green Revolution. So in the Green Revolution, when they could develop tube wells, or they had tube wells, they could irrigate the field, and they changed from a maize-wheat cropping cycle to rice-wheat cropping cycle. And that's basically the time in the late 1960s and the early 70s, when people developed symptoms of selenium poisoning in that area at the study site. So what was clear basically, so what they did, the farmers, in India, they very closely work together with the Ludhiana, the Agricultural University in Ludhiana. So whenever they have experienced any issue with their soil or their water or plants, they go to the university and ask for help, and they do the analysis for them. So what turned out that the selenium is in the soil, but and what they found is, okay, we know selenium is sitting in the soil. And what they did, they grow what I said, wheat. And the time when I visited the field site, they were growing wheat. That's the farmer holding a wheat plant. And you see all the leaves from the weeds are turning white. It's called white selenosis. So that's because it's caused by the accumulation of a lot of selenium in the plants. What they used to do in the past, I don't think they do that. They used to feed it to their livestock. And it also has, the selenium was in such high concentration that it caused selenium poisonous for the livestock. So you see this cow, the cattle here, which I think the photo was taken in the late 1970s. And you see the deformity of the cow, and the hoof were deformed. And then later, it also turned out that so the products eaten from the cows, the milk, the cheese, or even the meat, had still very high level of selenium, and it led to poisoning of the humans. And you see here they had bloody nails and they lost hair loss. So the question, okay, we have the selenium in the soil, and it happened during the Green Revolution that people experienced they were poisoned by selenium. So, but the question was, is the soil the source or the sink of selenium? Because either selenium was always in the soil and the irrigation changed the chemistry and made it more bioavailable, or the water carries the selenium, and that should be highly bioavailable, and then plants can take it up to a level where it becomes toxic for humans and for the livestock. So what I did, basically, I went there with my collaborator from India, Karaj Dalon. Here he's sampling water samples. So we collaborated with the farmers. So we took groundwater samples, which is basically the irrigation water, and we analyzed the selenium species in the water, if it's selenium 6 or selenium 4, and we measured isotopic composition. We also took soil profiles, 3 soil profiles from the field, where we analyzed the total selenium content in the soil, and then I did the sequential extraction, looking at the different selenium soil pools. So looking at the bioavailable selenium and the isotopic composition, and the adsorbed selenium and the isotopic composition. And I'm not measuring it here, but also selenium and organic matter in the soil. So these are the 3 soil profiles we took. What we see, so we divided basically the soil profile with up to 1, so we took a profile to 1 meter depth. We divided it into 6 intervals. I mean, we already have heard that most of the selenium seems to be in the top soil, so that's why we have smaller intervals in the top compared to the bottom. So the concentration, the total selenium concentration, you can see here, ranges between 2 milligram per kilogram for the soil profile on the right, to up to 4 milligram per kilogram for the one in the middle. But for all of them, it's the same, that below 15 centimeters, the selenium concentration drops drastically, and then it's basically almost no selenium at 1 meter depth. So the question is, what causes the enrichment of selenium in the topsoil? So then, therefore, we looked at the different selenium in the different soil pools. So we have the diamond one, the green diamonds one, are the water-soluble selenium, which is basically the one which should be the most bioavailable one. And the blue squares are the adsorbed selenium pools, and the blue diamonds at the top with the dot in the middle, that's the groundwater concentration. So concentration from basically from the left to the right increases. And what we see that the concentration of the groundwater first is like in the same range as it is for the bioavailable and adsorbed pool selenium. And what we see that what we observed is basically the irrigation water has only selenium-6. That means the most oxidized form of selenium. That means the most bioavailable one and most toxic one. And then, but still, we see that at the top part of the soils that selenium for these two pools is higher than in the other three soil depths for 11 to 42 and 42 to 70 and 70 to 100 centimeters. But still, it doesn't tell us much because we cannot still not understand the process behind it. So therefore, we look at the isotopes. So this is now the profile for looking at delta 8276, and if we look at the left of the graph, that's like enriched in lighter isotopes, versus if you look to the right, if you follow my arrow here, it's enriched in heavier isotopes. So what we see basically is that the blue square ones is the adsorbed pool, and again the diamond green ones are the bioavailable selenium. And what we see is bioavailable selenium is always isotopically heavier than the selenium, the adsorbed selenium in the same soil depths. And that's actually we see for all the three profiles. So from there we have the hypothesis that the irrigation water, which has this highly bioavailable selenium, selenium-6, is basically the bioavailable selenium-6 is the reactant, comes to the soil. In the topsoil, it gets reduced by microbes, probably microbes, most likely because it's an oxic soil. So it's getting reduced to selenium-4, and selenium-4 is then adsorbed in oxide minerals because it has a strong adsorption affinity to oxide minerals. So that means that the bioavailable selenium-6 should be always heavier than the product of the adsorbed selenium. Okay. Then what we did is basically we did a simple mixing reduction model. So if they irrigate the field, they bring in always more selenium that has an isotopic signal. It mixes with the pool in the soil. So then we did a mixing to account for that. We did a mixing model that's basically this equation here, and what you see, we have all parameters are measured. And then for the reduction, so that's what we are interested in to look at. So it's basically, we have all values we have measured. Then we have here the epsilon values, where we use an epsilon value for which is the isotopic fractionation of 10 per mil, which would cover if it's microbial reduction or if it's abiotic reduction is about in the middle. And the only parameter which we don't have any information, it's basically the extent of reaction, and we solve the equation to determine the extent of reaction for reduction basically in the soil. And that's what we got. These are the same three soil profiles. Again, on the top, the axis is like negative values as isotopically light, then positive values isotopically heavier. So then the blue squares are our measured adsorbed selenium pools. And when we would have only isotopic mixing, then our values should follow this dashed line here, but it doesn't. So, but if we resolve it for the reduction of selenium in the topsoils, then this is the model value, is the red line. And what we see is that about 7 to 60% of the selenium which is introduced to the soil by the irrigation water is going to get reduced in the topsoil. So now imagine you do that over and over again. You irrigate the field, you slowly accumulate selenium. Of course, part of the selenium coming from the irrigation water will be taken up by the plants, and plants will be removed. So not everything which is in the irrigation water will be in the topsoil. But that's basically, if you do that for 40 years, you will end up at some point having 2 milligram per kilogram to 4 milligram per kilogram selenium in the topsoils. So to summarize, basically for that study, is like we can clearly now say the soil is definitely not the source. It's basically the sink, and the irrigation water is the source of selenium, and it contains selenium-6, and selenium-6 is then reduced in the topsoils to selenium-4, and the selenium-4 is then adsorbed on oxide minerals, and about 7 to 58% of the selenium is reduced in the topsoils. Okay, so now moving to the second study. I think I need to hurry up a little bit. Okay, so the second study where we use selenium isotope as an indicator for post-binding selenium reduction in a uranium roll-front deposit. That was a study I was part in. It was with Berkeley Lab and UC Berkeley, and in collaboration with Illinois, Los Alamos, and EPA. So how is selenium associated with uranium roll-fronts? So what you here see in this cartoon is basically we have an aquifer, and the flow of the stream is going from the left to the right, and rainwater brings in oxidized anions. This could be uranium-6, selenium, molybdenum, arsenic, so whatever, in very small in very low concentration, and it carries along the oxic aquifer until it hits the redox front. That means it's more the EH condition redox potential drops, and then some of the then slowly, gradually, the elements get reduced, and selenium basically gets reduced and enriched here. And that's how it looks like, how these roll fronts form, depending on the EH-pH condition. So it would form first, we have, let's say, iron reducing condition, then we have selenium reducing conditions reduced here, then you have uranium is following selenium reduction, so you need more reducing condition to reduce uranium, and then further down gradient here, you would have sulfide reduction or then even methane. So what we basically did is at a field site in Texas where they have uranium mining. You see that here where the stars in the map on the right, and on the left you see basically that's a map for the wells we sampled. So we sampled wells, they are up gradient, some wells they are in the ore body, and then some of the wells are down gradient. And then we measure the concentration of selenium and the isotopic composition. That's the same map again. It looks a bit busy, but this map now includes the concentration of selenium-6 and selenium-4 in the water. We measured for the up gradient in the ore body and down gradient wells. Just to summarize quickly, we have much more selenium-6 in the up gradient wells and in the down gradient wells. We have up to 300 micrograms per liter selenium. And then in the once it hits the reducing front, basically we have very low selenium concentration and basically almost no selenium-6 anymore. In some of the wells, we still could observe selenium-4. But still, we don't know if that's reduction. So, but if we look at the isotopes now in this plot, so this plot shows you the isotope ratios we measure between -15 +15 per mil, and these are for different environmental samples. It has igneous rocks, hydrothermal system, marine shales. And on top you see here, these are the samples from our field site. So we have selenium-6, which are the light green circles, and selenium-4, which are the blue circles. And the yellow dashed line in the middle is the bulk earth composition for selenium. What we see here is what we can say that selenium-6 is always isotopically heavier than selenium-4. So what's basically mean that selenium-6 would be what we saw before for the study in India is the reactant, and selenium-4 would be the product, and the product becomes isotopically lighter and the reactant is isotopically heavier. So now let's look at this plot, which shows you selenium-6 concentration in the different wells we measured versus the isotopic composition. And for some of the wells, we clearly can see we can derive an isotopic fractionation factor, epsilon, which is the dashed line here, and we get an isotopic fractionation for a reduction of minus 2.3 per mil. But you see that not all of the samples fall on that line. For the ones in the gray circle here, you see they're falling off this line. And oops, sorry. And that clearly tells you that in these wells, there is no reduction. It seems to be more a dilution effect. So it's interesting to late, basically that's very important. If these wells might have to be monitored a longer time to see if reduction is happening or any other processes. So basically, these seems to be safe wells where reduction of selenium is happening. These ones, most likely not. And it becomes even more clear if we look at a transect. So we have a well which is up gradient, it means oxic, then in the ore body and down gradient one. And what we see, we have an isotopic composition of 2 per mil in the up gradient one, and in the ore it becomes really heavy of 6 per mil, so it becomes isotopically heavier because it's selenium-6, because it's the product. And then if we are down gradient here, we don't even have any selenium, and that's for this transect. It's clear we have selenium-6 reduction. So to summarize it quickly, so we have selenium selenium-6 and selenium-4, they are oxidized during the mining processes in the ore, but Anirban will tell more, but that's why I keep it short later about that. So then they get reduced, and then they lead to the enrichment of isotopically heavy in the reactant. And so basically looking at the isotope, we can trace if selenium reduction is happening in these wells or not. And to make it even clearer, we did a cross-well test. So what we did in one up gradient well, we injected selenium-6 and bromide as an inert tracer, and then the groundwater traveled through the ore body, which is basically here, that's the ore body, and then down gradient we sampled at different times. We sampled water and looked at how much we looked at the selenium and bromide. So what you see here in this graph below is time, and you have the bromide concentration, selenium concentration. So after about 10 days, we get the bromide signal is breaking through, and we know we catch the selenium peak, and that comes basically from the injected selenium-6. And then we did a speciation for the selenium in the water we collected from the crosswell test. So we have selenium-6, and we see that selenium-6 after 10 days starts dropping down to, and then on the same time, selenium-4 seems to increase, so over time. That means that's the reactant, and selenium-4 is the product of selenium-6 reduction. And if you would look at the isotopes, what would we expect is when we have, again, the fraction of selenium-6 remaining, if it's basically reduced, so it's like 0% reduced or 100% remaining, and then 0% remaining, then selenium-6 should be becoming isotopically heavier with time, but also selenium-4 should follow and should become isotopically heavier. And the distance between these two here, the offset between these two, basically should give us the isotopic fractionation factor epsilon. And this is from our data. So we have these, again, in the background, the lines are the concentrations, and there's squares and the circles here, open circles and open squares are the isotopic values we measured. And the offset between selenium-6 of the blue square and the red circle is always about minus 2.7 per mil. And then I just put it in quickly, but we're still working on that, on a reactive transport model, and this reactive transport model accounts for the rapid advection of selenium-6, the slow reduction of selenium-4, and the sorption of selenium-4, and the desorption of selenium-4. And basically the cross and are the measured selenium-4 concentration and isotopic composition, sorry, and selenium-6 measured values. And our model basically reproduces that very well if we have an in-string isotopic fractionation factor of 8 per mil. And that would reproduce the value of about getting to the 3 per mil, what we observe when we just do the offset measurement, basically. So to summarize this one, basically what we see is our cross-well test shows us the same fractionation, then gives us the same isotopic fractionation than the well when we look at the field observation. Basically, we can compare them, and we clearly see, okay, for the isotopic fractionation, for selenium in the field is about minus 2.7 per mil. So if we get something like that, then we can clearly say that selenium reduction is happening in these wells. And so both we get to summarize similar isotopic fractionation for the field observation and the experiment, and we can, and our well data support selenium-6 reduction and the natural remediation in these row fund ore deposits for selenium. And I quickly would like to thank these people which were involved in the study. And I thought I add one slide because Anna said something maybe about human health, and no one has done that yet. So I had to come up with something. So how we can use selenium stable isotope to trace the human health status. And that might be possible because we can look at how selenium might be absorbed in the human body, and we can trace, looking at the isotopes, if someone has deficiency toxicity effects in expression of different of the amino acids, because what the figure on the right shows you, if we are in a healthy system, the variation, the status. So if you have a selenium status of 0 and the cells takes up selenium in a certain amount and the excretion is much smaller, and then when we look at this disease system, either deficiency, toxicity, cancer, or any other diseases, then there might be an offset compared to the healthy system. But that's something I would like to develop more, and that's I think we would like to brainstorm about it later. And yeah, I would like to thank you, and I think I'm not over the time yet. That's great. Okay.
Good. Thank you, Kathrin, so much. Thank you. And yeah, we have like 7 minutes, 6 minutes or so for questions. So that's great. And we already have a few in the chat that you can start reading and looking at them. Yes, and maybe, but Ben, if you would like to ask your question, if you can unmute yourself.
Yeah, I was curious about the effect of substitution on the fractionation factors. The fractionation factors that you report are assumingly for pure selenium undergoing redox changes, but especially if there's elemental selenium as an intermediate, and it has forming a solid solution with elemental sulfur in the same systems, how does that impact the fractionation?
With elemental sulfur?
Yeah, because it combines with elemental sulfur, and elemental selenium are essentially miscible.
But there should not be any fractionation between that.
So it doesn't affect the fractionation at all?
No.
Great.
No.
I'm just curious. Thank you.
Good. So Lex, would you like to ask your question?
Sure. Thanks, Kathrin, first of all. My question is about the profiles of concentrations of selenium in the soil, and you also added a symbol for the water. And I had trouble understanding what the units were. Water being measured per volume, soil presumed per mass. And so you were making a statement about the water being a source, but somehow you need to do some sort of mass balance. And I was wondering what I'm missing there.
Oh, you mean so the soil is measured in ppm, and the water was measured in ppb. And for the soil fractions, for the soil pools on the plot, they were reported in milligram per kilogram, ppm, and also in this, the water was in ppm because they have about 0.6 ppm selenium.
So
I understood your question right, sorry.
No, well, maybe I didn't present it clearly. When I think of soil and water, I mean, obviously in the context of arsenic, which is what some of us have been studying for a while, you know, I think about how much water is needed and how much selenium there is in there. And so you get a certain amount of selenium, or of arsenic, and you could do it for selenium. And I compare that to the buildup of either arsenic and selenium in the soil. And I try to compare those two. I don't think the elements you gave us in the graph allowed us to do that, did it?
No, because it's like, it's not, I'm not measuring, I did not report that accumulation over a certain time, like looking at year 1 and year 2, or like season 1 and season 2. It's just like a one time, we took samples from there to understand if this can be, because the argument was that the alluvium carries already the selenium in the soil, and then the water remobilize it, and we just wanted to see basically, can that be the case or not? And when we look at the isotopes, that cannot be the case. So how much is so the accumulation, what I just said in the model, is basically on one-time irrigation. Of course, that doesn't account for how much can be taken up by the plants, because the plants also take up a certain amount of selenium from the irrigation, and they only irrigate the field during the rice season. So that might also change, and that every farmer might do that differently, how often they irrigate the field. So I have to account for that, how often they do that. But that could be just, the model can just tell you that's the amount which is possible to get reduced by the condition in the soil. But then it depends on how much can the rice take up, and then the rice volatilizes the selenium, and then the selenium, basically, because it doesn't travel far, is going to get back to the soil. So, yeah.
Okay, I should read your paper more carefully, and hopefully I'll figure it out. Thanks.
Okay, so we have 2 more questions in addition to the one I had, but let's go to the ones that from others. So maybe, I don't know, maybe the Steve Spade question is kind of related to the current paper, so that Alex's question was about. So Steve Spade, would you like to ask your question?
Sure, thank you, Kathrin. My question is, if you wanted to remove selenium from the irrigation water, is there a recommended water treatment technology?
You can add, if you can add in the well, zero-valent iron, maybe, or something, and reduce them before you pump it out to the on the field. That might be something you can add. But they really don't do anything there right now, to be honest. Yeah.
And then Steve Chilrod has another question that I believe is from the second paper. So Steve, would you like to ask?
Sure. Yeah, nice talk. I had 2 quick questions. You know, one was just a general chemistry question, whether the selenium forms the equivalent to the thioarsenates, the way the sulfur thio complexes form.
I think it does.
Okay.
But
yeah. The second question is straight from your injection experiment. You know, the reduction in concentration of the selenium-6 was much larger than the increase in selenium-4. I assume that's because the selenium-4 is absorbing to the
either absorbing, or it's also further reduced to elemental selenium at the same time. So that's why it will never reach the same level as it. So once you have selenium-6 reduction, selenium-4 kicks in, then basically selenium-4 is then also reduced further to either elemental selenium, or it's absorbed. Yeah.
Do the isotopes help you distinguish between those two, or?
Then you need to look at the solid phase in the ore to look at if you have elemental selenium. But it looks like you see that the isotopes become heavier for the selenium-4 as well. So it seems like it's getting reduced further because it's an intermediate product that basically becomes isotopically heavier because the lighter one goes to the solid phase.
Okay.
Otherwise, if it's adsorption, it would probably level out at one isotope.
Well, great.
Okay, so thank you, and we are perfectly on time, finishing our first talk. So this is great. Thank you so much, Kathrin. And normally, under our regular seminars, we will have 5-minute break, and we would have some coffee, do some chit chat for the people in the room, and have the opportunity to interact among each other. And we would take a picture with the speakers and all of that. Unfortunately, in our remote version of the seminar, we cannot really do any of this. So I don't think there is a point for us to wait in 5 minutes. Those of you who need to take a little break can do it anyway at any time when you want. So I think we should just go ahead. And maybe, Kathrin, if you can stop sharing your screen.
Yes,
and
sure.
Our next speaker can, anyone can start sharing his screen. And Steve Chilrod is going to introduce Anirban. So Steve,
Okay.
I let
We need
you.
to just change the place because
We need to change speakers and change the slides. Wonderful.
Away my joke. I was going to see if anyone noticed the same background.
sorry.
Anyway,